This supplementary lesson consists of 3 differentiation rules and their applications. Product and quotient rules, which are covered in 3.2 of our textbook, and the chain rule, which is covered in 3.4. But before those, let's talk about elementary derivative rules, just for review. Here's the way we define the derivative function. This quantity over here is called a Newton quotient. Geometrically speaking, this is the slope of a secant line. By taking the limit, we get the slope of the tangent line for given x value, and then changing that x value around, we get a new function given by the slope of tangent line for arbitrary x values. That function is called the derivative function. Calculating the derivative function or derivative value using this limit computation and limit rule is going to be very, very challenging. Consequently, most of the time, we rely upon these formulae. The derivative of constant function is 0 because we have a horizontal line which has slope 0. The derivative of sum is sum of the derivatives. If you have coefficient, then you can multiply either before or after. The power rule for power functions, exponential rule for the natural exponential function, logarithmic rule for natural logarithmic functions. Notable extensions: if you have arbitrary base, then you'll have to normalize by multiplying by log of a or dividing by log of a. However, these extensions are going to be minor issues actually, because once we go through the chain rule, these will turn out to be rather trivial and very impractical actually. Too many formulae to remember for nothing. So we're going to rely upon less of those, and we're going to stick to natural exponential and natural logarithmic functions most of the time. Here are some examples that we can do with those elementary derivative formulae, and let's do these very, very quickly because we've done all these already. How about the first problem? Well, it can be confusing, but please note that this is an exponential function, that's a constant, and everything else is a power function. So we can apply the exponential rule. Constant is 0, and then everything else just power rule. How about the next problem? We have product of 2 functions. So do we multiply the 2 derivatives? No, we can't. We can add the 2 derivatives if they added together, but not multiplication. So this is what we do. Break up all those parentheses by standard expansion technique. Take the like terms together to simplify, and then apply the power rule one step at a time. The similar kind of argument applies for quotient. Do we take the derivative of numerator and derivative of denominator and simply take the fraction of them? Not really, we can't do that. We'll have to find a way to separate them and then use power rules. So here we go. You can separate the numerators because denominator is simply monomial, and then simplify everything to get a bunch of power functions added together, and then we can apply the power rule one at a time. Alternative way, alternative way, we can multiply by the power function with negative power. That's the way we change division to multiplication, and then use distributive law to expand everything out, and then do the same thing. Now, we could do these kind of expansions to product and quotients because the product and quotients were rather simple in this case. However, if those are rather complicated, then we're going to need fundamentally different tools, and there they are actually. Here are some motivational examples, and then let's look at this one, for example. And the first one is actually easier, but this one fits our purpose a little bit better because this is all power functions actually. So it is possible to express everything into power function and then expand everything out and apply the power rule one step at a time. Yes, we can do that. However, if we go over to something like this, we can't do that because exponential and power functions are jumbled together. Exponential and logarithmic functions are jumbled together. Here we have subtraction or addition in denominator. We can separate the numerator, but we cannot separate the denominator. So we need fundamentally different rules, and there they are. The product rule and a quotient rule. Product of derivative of product, derivative of uv, is u prime v plus uv prime, and then the derivative quotient u over v is u prime v minus uv prime over v squared. As a matter of fact, this is a little bit difficult to read, so let me expand the font just a little bit. I hope this is better. And please note that the product rule and the numerator of the quotient rule are more or less identical. Same order and everything except for the sign, the negative sign versus positive sign, and then of course the denominator, this conspicuous denominator. I've seen a lot of mistakes from students on product rule and quotient rule since I began teaching calculus in 1994. But I have never seen a student missing this conspicuous denominator v squared in quotient rule actually. So that's no big deal. Overwhelming majority of the mistakes were coming from the order of this u prime, v prime, u, and v. Which order are they multiplied and added? Consequently, you have to be really careful memorizing these formulas accurately. And for that reason, I'd rather emphasize my convention over that of the textbooks. What am I talking about here? If you look at this numerator and the product rule, they're more or less the same. So basically, if you follow this convention, you have only one rule to remember, as a matter of fact. If you use the textbook's notation, if I remember correctly, they use this convention. uv prime minus vu prime plus vu prime, I think. And then for quotient rule, I think this is what they use. vu prime minus uv prime or something like that. And I found those two. These are textbooks notations, by the way. I found these two very difficult to follow because basically you have to remember two different formulae. They are very much alike, and I think that's going to cause a lot of confusions. I've seen a lot of mistakes teaching these topics, and if I'm not mistaken, this convention that our textbook is employing is directly responsible to a lot of mistakes, and maybe a lot of students ended up getting C instead of B and so on. Consequently, I'd rather emphasize my convention here, u prime v plus uv prime, and then u prime v minus uv prime, so that you have only one thing to remember, and just everything is consistent from that point on. Denominator is so conspicuous, nobody misses it. And how about this plus and minus? Well, after all, this is multiplication versus division and their inverse procedure, and plus and minus their inverse procedure, so they make a lot of sense in terms of common sense argument here. The second reason that I prefer my own convention will be discussed in 2.3, but we can discuss it later. Let's go ahead with an example. So let's go ahead with derivative problem for this problem, but as usual, let's change everything into power form. That is the starting point of a lot of problem in calculus. Here we go. So we have product of two functions, and all those are power functions added together. Alright, and then what is the derivative function if you use the product rule? And this is the way I would rather recommend. Instead of just going ahead with the derivative computation, get the structure of the product rule first, and then do the derivative computation one at a time. So the structure of the product rule is done. u prime will be filled up here, and then v, you can just copy that, plus u, I just copied and pasted, and then v prime will be filled up right here. So the structure of the quotient rule is already done, and now let's go over to the derivative problem for u and the derivative problem for v. In short, what I just did was to reduce this one complicated problem into two simpler problems, number 1 and number 2. How about number 1? Okay, let's go ahead. Derivative of x squared, 2x. Derivative of 3x, that's 3. The derivative of minus 4x to the negative third power plus 12x to the negative fourth power. So that comes from the first function. And then let's move on to the second function. Okay, that's gonna be 2 times x to the negative 1/2 power, because I have to subtract 1 from the power, minus 1/4 times 1/2, so this is gonna be plus 1/8 x to the negative 3/2, because I have to further subtract 1 from the power. So here they are. We got the structure of the product rule first, this bracket and that bracket, and then took the derivative of this blue part and then the red part. And I'd rather recommend this step-by-step method to everybody. Of course, as you will get used to this product rule and quotient rule, you'll be able to just write it down from the start. However, at this moment, I'd recommend everybody to follow this convention. And this kind of thing, I'm getting the structure first, and then take a deep breath, and then going over the smaller problem, and then another smaller problem, will help you a lot when your computation problem is far more complicated. Especially after this chain rule, when 3 derivative rules are all jumbled up and when we have enormously complicated problems, then instead of trying to do everything all at once, reducing it one step at a time is usually a good idea. And then this kind of bracket, and then enough spaces to put the derivative, to get a structure, is a very, very good way to reduce your problem. Let's do something similar to the quotient rule here. Let's go over to the last problem. H prime of x is gonna be equal to that. And then, as usual, the conspicuous part, denominator squared. And then we have derivative of numerator times the denominator minus derivative of, just numerator times the derivative of denominator. That's the way we get the structure of the quotient rule. Let's expand the fonts just once more. So u prime v, u v prime, and then we got this part and then that part to fill up. So in short, we got the structure of the quotient rule first, and then we are going over to the derivative computation. Now, what is the derivative computation here? What is the derivative of the numerator? 2x plus exponential function stay the same. U prime v minus u, and then let's go over to v prime. What's the derivative of x? That's just 1. What is the derivative of log of x? 1 over x. And that concludes the derivative computation problem.